identify whale-generated sounds from oceanographic data, focusing on binary classification, which is whale and non-whale sound. Previous research on whale sound identification has explored both manual and automated approaches. Traditional methods such as boat surveys, sail drones, and hydrophones have provided valuable data but often invasive, labor-intensive, costly, and dependent on weather conditions. More recent efforts have applied machine learning to images and videos using techniques like convolutional neural networks, support vector machines, and satellite imagery for whale identification. These face challenges including poor visibility, lighting variability, species differences, and data standardization issues. Oceanographic acoustics, particularly passive acoustic monitoring, is effective in harsh marine conditions and leverage acoustic signatures for species identification, but requires advanced signal processing skills and handles complex data sets. And the table 2 also exhibits the existing tools and solutions for whale identifications which were used. There are also a number of tools and solutions already in use, and our goal was to build on these efforts using advanced machine learning to improve accuracy and scalability. When coming to the key takeaways, Raffam's 1996 work noted that whale sounds have musical structures. This insight led us to apply music information retrieval techniques to extract features from whale songs. The field is evolving from manual, invasive processes to automated, non-invasive methods powered by machine learning, which are more scalable and ethical. The significance of our approach is that it supports non-invasive monitoring and avoids the need for physical tagging. It helps conservation by enabling accurate detection of whale presence using existing acoustic data, which is more cost-effective. We combined marine science and machine learning to develop a scalable solution. We also address data imbalance to improve detection of rare whale sounds and set the stage for potential real-time detection systems. When moving to the methodology, we use data from kernel whale detection challenge collected with hydrophones, which is elaborated in this particular slide, and we extracted features like tempo, beats, chroma features, and MFCCs. The model we used was XGBoost, trained in an 80-20 split with tuned hyperparameters. To address class imbalance, we applied random oversampling, synthetic minority overlapping technique, which is called as SMOT, an adaptive synthetic sampling approach, which is called as ADASYN, and compare their performance. Here shows our correlation analysis, which shows that rhythmic and tonal features were strongly linked. For example, tempo and beats had a correlation of plus 0.84, while chroma features were strongly tied to energy and brightness in the audio. MFCCs were highly correlated, confirming their relevance, and these insights help us to choose the most useful features for classification. Moving to the results, out of the shown attributes pairs, we had to drop some attributes to mitigate the multi-collinearity. So you can see that this table consists of the attribute pair, the dropped attribute, and chosen attribute. For example, out of beats and tempos, we had to drop beats and to choose attributes. So table 5 and table 6 shows the particular training and testing accuracies. And here the model performance after applying SMOT can be shown, and the model performance after applying ADASY, and the model performance after random oversampling. When we are coming to the overall idea, the model trained with random oversampling achieved the highest precision for class 1, effectively minimizing false positives. ADASYN provided the highest recall, indicating stronger detection of true positives, Both random oversampling and SMOT reach an overall accuracy of 93%, while Adazine slightly lowered accuracy to 92%. Among the techniques, random oversampling offered the best balance between precision and recall, making it the most reliable for identifying the whale vocalization. So, hyperparameter tuning with random oversampling led to the optimal XGBoost configuration. So we've been using subsample of 0.8 and 1000 N estimators, and we had a learning rate of 0.2 and the particular hyperparameters as shown in here. This setup achieved a validation accuracy of 97%, showing strong generalization. On the test set, class 1 recall improved to 71%, class 0 precision reached 96%, and class 0 recall was 94% as well. Tuning enhanced whale call detection, though the model still performs slightly better on the majority class, so that is anthropogenic acoustics. The best performing method was XGBoost with random oversampling. It achieved 93% accuracy overall with a 63% F1 score for whale class and a recall of 71%. This demonstrates that balancing techniques and hyperparameter tuning are essential for reliable detection of whale vocalization, especially in noisy marine environment. When coming to the conclusion, in a summary, acoustic monitoring provides a non-invasive, cost-effective alternative to traditional methods. Our machine learning model performed well, achieving 93% of accuracy. The approach is adaptable to different regions and potentially other species as well. However, we were limited by small sample size and did not yet distinguish between the species. Future work will involve larger dataset species-specific identification and real-time monitoring systems. These are the references that we have gone through. And thank you.
Thank you for Dr. Haruni Perez. So any questions or comments for Dr. Haruni Perez? Okay, I will raise a question. I think this direction is very interesting. So you have talked about the imbalance data set. You mean the positive data set is very small compared to your training data set. So how do you deal with the imbalance issue of the data set? Thank you.
So there we had to do the data balancing because there was, as you mentioned, there was a huge data imbalance. So we had to go through the data balancing part, as we have mentioned in the presentation, that when we move to the methodology, that data preparation, so we had to normalize the data from feature scaling, and we had to do the correlation analysis to retrain the most relevant features.
Okay, thank you. So if no more question, let's move to the next presentation. The title of the next presentation is Personalized Multimodal Emotion Prediction, presented by Dr. Uchari Taraka. Let's welcome.
Hello everyone. Today we'll be presenting our research on personalized multimodal emotion prediction. So this project tackles a key challenge of capturing the individual differences in emotion expressions. So talking about the problem background, human emotions are deeply personal and expressed differently by different individuals. To express how we feel, we use multiple modalities like facial expressions like vocal tone or speech content. The challenge is that each person relies on these modalities in unique ways, and in those proportions can change time to time, maybe depending on the context and the situation, it differs. So, for example, if you know this character Early Bachman from Silicon Valley, he verbalizes his emotions very explicitly. In contrast, Mr. Bean expressed everything using only facial expressions and gestures without even a single word. So now you see the challenge. Problem is that system models often fail to consider these personalized time-varying modality proportions. So what we propose is an ensemble model that learns personalized data and adapts to user-specific emotion expressions. So it dynamically captures which modality is more influential for each user and adjusts accordingly. So, this kind of personalized models can improve several fields like recommendation systems, customer service bots, or target marketing, and there are so many things. So, in our solution, we focus on three modalities: facial expressions, vocal tone, and speech content. And we categorize these emotions into four classes: happy, sad, angry, and neutral. Our solution consists of two key phases. The first one is training individual models, and the second one is training ensemble model, combining those three individual models. So, this ensemble model learns how to weigh them based on user-specific data. And also we prepare two datasets for each modality. A common dataset which used to train base models and a personalized dataset for fine-tuning purposes. So each model was trained and evaluated independently, so we could assess its performance and the contribution. As example, for text, we used Twitter dataset and Distilbert model. For vocal tone, we used Crema dataset with MLPs and CNNs. And for facial expressions, we used FER 2013 dataset with MobileNet, ResNet, and VGG60. Talking about the training workflow, we first trained each model using a common dataset, then tested it on both common and personalized test datasets. So after that, we applied incremental learning using personalized data. After applying the incremental learning with personalized data, these accuracies improved significantly. To continue the presentation, now I invite Vijay.
Okay, so let's move on approach of our ensemble models. So as explained earlier, we initially trained three models individually using a common datasets. Then we assign weights for each model. And we use personalized data for emotion prediction, where the final prediction was based on a combination of the individual prediction and the assigned weights. After each prediction, the model weights were updated based on accuracy. Finally, we used the same personalized datasets to further train models using incremental learning. This is our proposed architecture. Initially, the model receives personalized data and produces probabilistic predictions for each emotion class. We started with constant weight values for each model. These weights are adjusted, increased or decreased based on correctness of each prediction. Once each model is trained on its respective personalized datasets, we combine all the personalized data samples and train the models further using incremental learning. For the personalized datasets, we use 600 samples, like 200 per each model. The overfitting was the major concern, so we added noise to each vocal tone datasets and change image backgrounds as much as possible to generalize the data. We experimented with two weight updating mechanisms, updating weights at a constant rate and updating weights based on the current accuracy for each model. By looking at these results, we saw that the second method, which is updating weights based on current accuracy, gave the best performance. And talking about experiments and analysis, so this slide shows how weights change over the time during the prediction. When using constant rate update, weights for text and vocal tone increased, but weight for the image model decreased. However, with the accuracy-based updating, all weights increased, leading to better overall performance. Let's now look at how incremental learning affects the prediction. Initially, weights decreased over multiple predictions, but after applying incremental learning, the weights values is starting increasing, reflecting better adaptation to personalized data. So talking about difficulties, one of the key challenge was overfitting. To mitigate this, we created three distinct personalized datasets and generalized them using techniques like adding background noise, changing images backgrounds. So this helped to improve model robustness. So talking about the results and analysis, we show the prediction accuracy for each sample. An important observation is that the final weights varied from person to person. This helps us to understand how each modality uniquely contributed to emotion prediction for different individuals. So let's move on to the discussion. The three main factors influence how weights assigned to each model: the number of trained samples, the richness of class-defining characteristics, and the model's performance. So ideally, we expect only first two factors, data quality and quantity, to affect the weights distribution. This becomes a challenge because if a model is given a rich and sufficient datasets, it may still receive lower weights if it fails to perform well. As a result, the effectiveness of training data is limited by the model's ability to learn from it.
Okay, thank you, Zula. With that, let's move on to the demonstration. For the demonstration, we have developed a web application where we can use a video clip to create the read sample and then use that read sample to test our models and at the same time to monitor the learning curve and the accuracy of our models as well. So here's the web application. So I have 4 video clips of the same person with four different modes. So it's the angry one, the happy one, and sad video clip as well. So I uploaded 4 video clips. Now I'm going to create the read sample by splitting this. So here you can see the read sample is being created. Now I'm going to shuffle this read sample multiple times, and now I'm going to predict the first read sample. So as soon as I click on this predict button, you can see in the backend it starts predicting the read sample, and then it will learn using the read sample as well. So down here you can see after the read sample is being predicted, you will see 4 lines. 3 lines are showing the accuracy of the 3 modalities, and then the 4th line will show the prediction of ensemble model as well. So it takes some time. Because of that, I'm going to send multiple data samples in one go. So it will predict one after the other, and then it will use one after the other for learning as well. So I clicked on this predict button, and in backend you can see it started the prediction. So until then, I will show you a few graphs I have already drawn using the same process. So these are the sample graphs. Here you can see this pink line is for the vocal tone, blue line is for the image model, the green line is for the text model, and this red line is for the ensemble model. So as we may have already mentioned you, different people use different modalities to express their feelings. A certain person may use vocal tone to express his feelings. Another person would use his facial expressions to express his feelings as well. And not only that, even the same person might use different modalities to express their feelings according to the situation as well. So the first point I wanted to highlight is that our model cover all these 3 modalities. So whoever the person, whatever the situation, and whatever the modality is using to express his feelings, we cover all of them. So our ensemble model knows how to get the best out of his expression, whatever the modality he is using. So that's the first point I wanted to highlight. And then the second point, you can see here, this graph shows that text model performs well. It has the highest accuracy. But here you can see the vocal tone model has the highest accuracy. So what you can see, like different models have like different accuracy levels. The point is, whatever the accuracy they have, all 3 models are increasing its accuracy. Let's say the image model might have like less accuracy, but still it is increasing its accuracy. That's because of the online learning. That's the second point. And then the third point, you can see here, as soon as you look at this graph, you can see that text model is performing well. But after few samples, you can see ensemble has an even better accuracy. So in all these graphs, you can see after few samples, whatever the model has the highest accuracy, the ensemble model has even better accuracy. So let's say in this one, you can see text model has the highest accuracy. If you use only the text model to predict it, you can see at this point, the text model is predicting it in an incorrect way, but other 2 models are predicting it in a correct way. So our ensemble model, even though the best model is predicting it incorrect way, it knows how to get the best out of other 2 models as well. So our ensemble model knows how to get the best out of all 3 models and at which point. That's the third point. And the fourth point I wanted to highlight is, that's the extra point. So actually in this process, we are providing the original label as well with the data sample. We tell him that original label is happy. So after model is predicting the data sample, it will use that original label to learn. But in practical scenario, we don't have a way of providing that original label. So actually, if you look at this ensemble line, you can see there are very few examples of predicting incorrectly. So actually in practical scenario, we can use that like final prediction of the ensemble model as the original label. So in such scenario, you can understand that whatever the model that is predicting in a better way in that scenario, it is not only predicting well, it is not only performing well, but also it is supporting other 2 models to learn well as well. So finally, the 3 models together, the like large ensemble model, not only predicts well, not only performs well, but also helps each other to learn well as well. So with that 4 points, let's go back to the web application to see our graph. Okay, so it is there. You can see it's a pretty similar graph as we saw. So I have already described the points here. So with that, I can complete the demonstration and end the presentation as well. Okay, thank you.
Thank you. Thank you for all of the presenters. So any questions or comments for this presentation? Okay, maybe I just raised 2 questions. I think this topic is a very interesting. Giving the multi-modal input, we want to predict the emotion of the person. So Can we back to the slide 13? Okay. So my question is, you have used the multimodal features, right? So what is the encoders for each model, and how you to integrate the different embeddings from the different modality? Have you experienced the different integration methods to test the efficiency? Thank you.
Okay, so thank you for the question. You're asking about the weight, right? Weight updating mechanisms.
13, I think the slide 13 about the whole pipeline. Oh, previous one. Oh, maybe 11. Oh, sorry. Yeah. Okay, thank you. You
Okay,
have.
Okay, so I'll go through the architecture. So when it comes to the data sample, there are actually, even though we call it data sample, it consists of 3 data samples: image sample, text sample, and audio sample. So when we fed a data sample into the ensemble model, we actually fed 3 data samples in 3 modalities. So even though we call it ensemble model, it consists of 3 individual models: vocal tone model, image model, and a text model. So individual data sample will go into individual model. So it will predict the data sample and it will give a weighted prediction. And at the same time, models also has a weight. So depending on the weight of the model and the weight of the label, the prediction, the ensemble model will give the final prediction. So depending on the correctness of individual model predictions, we will vary the weight of the model. That's how it works.
Okay, thank you. So it seems that you do the integration after the model. So
Yes.
why do you do the integration, like combining the features from different modality before the model? How do you think about that? Because we already have several encoders for different modality.
I actually didn't get the question. Hima, did you get it?
Oh, I just repeat my question. I mean, from the architecture you show us, you do the examples of the different models. I mean, why you do the examples as a post-processing after the models outcomes, instead of do the combination before the models, like you use the encoders for the different modality input and use some network to concat the embeddings and use only one models. I mean, why you design the architecture like this? Yeah.
Okay. Yeah. I get this. So when it comes to a person, different people have, as we described earlier, as well, different people have different modalities that they use to express their feelings, and it depends on the time as well, the occasion as well. Even the same person might use different modality to express their feelings in a different position. So when we use 3 different models, which are uh, separate 3 different models, the individual model can perform better, right? So rather than using a combined model.
Thank you. And last question is about the data set. How many person the data has? I wonder I have the concerns about the diversity of the data set. I remember you just saw you got 3 persons.
Yeah, but for personalized data set, we create 3 data sets using 3 people.
Why not gather more data from the different person, like 100 people?
To be frank, the actual issue is it's really difficult to create data sets using personalized data sets. That's why, because we need all 3 modalities now.
Yes, ma'am. I have to add something. So although we are using data from 3% for the final model, actually we have for the pre-training on training the individual models, we have consider large data sets, and it consists of data from several peoples, like thousands of people, and they are common data sets. So in the basic stages, it has the knowledge from those data as well. And what we are doing in the ensemble one is combine preserving those knowledge and combining them and personalizing using that I mean these limited data from limited people.
Thank you. Okay, so any more questions about for this presentation? Okay, if no questions, let's move to the next presentation. So the title of the next presentation is Enhancing Lung Cancer Prediction Using Machine Learning, a comparative analysis of hyperparameter optimization techniques, presented by Dr. Lukshi Karanakaran. Thank you. Let's welcome.
Good afternoon, everyone. I'm Lakshi. Today, I will be presenting on my research to enhancing the lung cancer prediction using the machine learning. This works untapped potential of hyperparameter optimization technique using the numerical data. Here is the overview of the presentation file. I will begin with the background and related studies, followed our methodology and key result. Lung cancer is the leading cause of death global-wise and significantly lower survival rate. Conventional diagnosis method, the CT scan, is an expensive, time-consuming, and susceptible to human error. Machine learning and deep learning provide a cost-effective and automated approach to predicting the lung cancer using the numerical data, and also to evaluate the hyperparameter tuning and the cross-validation technique to enhancing the model performance. With the help of the existing studies, the primarily focusing on image-based lung cancer prediction to insufficiency of the numerical patient record and also lack of the comprehensive studies on hyperparameter tuning to impacting the performance of the machine learning and deep learning models. The current studies using the cross-validation models to reducing the overfitting. The gap is integrating the model's performance into clinical workflow and also addressing the computational efficiency in real-world application. The main objective to enhancing and accurating the lung cancer prediction to using the numerical data to optimizing the machine learning and deep learning techniques to checking the model performance to tuning the hyperparameters to boosting the model accuracy with the help of the cross-validation method to preventing the overfitting, and also to developing the cost-effective model to minimizing the imaging dependency for broader access. In our research focusing on lung cancer prediction using the numerical data. So, to the collecting the data set, that is the publicable data set, to using the hyperparameter tuning and also machine learning and deep learning concept to using the numerical data. the deep learning concept such as CNN, MobileNet, and Swing Transformer. The CNN architecture including convolutional layer, flattened layer, dense layer, and the mobile architecture including global average pooling layer, dense layer, dropout layer, and swing transformer is a max pooling layer, swing transformer layer, global average pooling layer, dense layer, dropout layer with the help of the Bayesian optimization techniques to finally getting the output. And with these machine learning and deep learning concept to checking first without using the Bayesian optimization techniques, using the cross-validation techniques, first checking the results, and then after applying Bayesian optimization techniques to checking the results, both comparisons of the results, the after applying the cross validation techniques, that is the improving the model performance, and then after applying the hyperparameter strategies in the testing draining accuracy values, the assembled models are achieving the highest results rather than other results. And then comparing that all the machine learning and deep learning techniques to checking the model performance, and then to checking the draining time values to less and highest values to in the machine learning and deep learning concept, and then checking the deep learning concept training and validation accuracy and loss with the epochs 10, which one is the most accuracy and which one is the less loss of the deep learning concept. Finally to including the evaluation metrics of the machine learning and deep learning concept to checking without the using the Bayesian optimization technique, and then after applying the Bayesian optimization techniques to increasing the model performance of the lung cancer prediction using the numerical data. Finally, the study demonstrated assembles model to getting the highest accuracy, and also in the deep learning model, the CNN showed the best performance to slide overfitting. So these results are getting after applying the Bayesian optimization techniques to significantly improving the model generalization and accuracy, and also the cross-validation method to enhancing the model performance to using the medical clinical setting. So in future, to efficiency improving the other deep learning concept, and also using the larger data set with the help of the transfer learning method to increasing the model performance to limited platform, it's including the edge devices to ensuring the real world applications. These are the references to refer on our research to checking the numerical patient record. It's available on in our existing studies. Thank you.
Thank you. Thank you for the presenter. Any questions or comments for Dr. Lokshi Karuna?
Okay, avulani
anyone? So any questions or comments? Okay, if no question, I have two questions. I think the lung cancer prediction is a very important and promising direction using the techniques of machine learning. So my first question is, the problem can be classified into binary classification? If yes, do you face the similar issue like the imbalance data sets? Because we know that only few people can got the cancer. So how do you deal with that? And second one is, it seems that you use a different model, a deep learning model like the CN, MobileNet, and Swing Transformer, and you use the Bayesian optimization to example the outcomes of them. So which one do you think contributes the most? Because we know that the latest achievement is transformer architecture. So can you share more insights of that? And thirdly is about you also mentioned about the transfer learning, because how can you regard the method if we got seem that we got very high frequency of the model prediction? So is that applicable to the real data? Do you have any experiments on the cross data validation? Thank you.
First of all, thank you for your questions. The first question you asked about the imbalanced event. How do you handle the imbalanced data? So here my data set is having the more than 5,000 data. So which is collected from the publicable data set. So I have to manage that data set with that help from the machine learning and deep learning concept. So that's why I'm better to improving that results, that imbalanced data set using that 5,000 records. But in future, maybe I collected from the more than about a larger data set, and with the help of also I have to decrease that imbalanced data set. And the second question is you asked from about the deep learning concept. So the deep learning concept here is I am using the convolutional neural network and mobile network and also the swing transformer network. But based on that, the deep learning concept, the CNN model is getting higher accuracy rather than that other two deep learning concept. So that's why it's on my research, the in the deep learning concept, the CNN model is getting higher accuracy rather than the two deep learning concept. In future, maybe increasing better, which means the you mentioned the transfer learning model. How do you apply that one? In future, maybe the vision transformer learning using maybe better than this deep learning or machine learning concept, we can applicable if we can applicable for that one, we can apply the transfer learning model in the future for the larger data set.
I mean, increasing the data set won't solve the problem of class imbalancing, because we get usually few cancer patients. Maybe you can do some kind of augmentation and generate more data on top of the available positive data of cancer data. Within even 5,000, you can do some to solve the class imbalancing problem.
Okay, you mean use generative models to generate the
Even you can do some augmentation.
augmentation?
Or maybe you
Okay.
can generate maybe artificially generated some generators also. They are now to generate some realistic data by using like giving some real data and ask them to generate the similar data sets.
Yes,
Okay.
thank you. I think it's a common issue for if we want to apply the machine learning to the real life problem, like the acoustic wheel identification, like the first presentation, and the third one that the lung cancer direction. But luckily we have the generative model right now. So how to combine the real data you collected from the real person and the synthetic data generated by the current generative models, I think very important and a very promising direction to discover. Yeah. So any more questions for this topic? Okay, if no, we will move to the next presenter. The topic of the next presentation is Lime enhanced sentiment classification for UI or UX improvement in Sri Lanka mobile ranking, presented by author Dr. Nirosana Karunanithithi. Let's welcome.
And today I am going to present my research title, Lime Enhanced Sentiment Classification for UI and UX Improvement in Sri Lanka Mobile Banking Apps. So here this is the structure of my presentation. And let's begin with the background to understand the content of this study. So in Sri Lanka, it is estimated that around 17% of the population use the mobile banking apps to access the financial services. As the number of continues to grow, having a strong UI and UX design is crucial. It not only builds the user trust and the satisfaction, but also help the developers provide the better updates. So in Sri Lanka, many users, especially the elder people, struggle to use the mobile apps due to the complex design. So the current app are often not user-friendly for all the ages and skill level people. Next, so we used Vader to measure the emotional tone of the user reviews. Then the topic modeling helped to uncover common hidden themes. To understand why our best model made certain prediction, we used the line to explain these decisions. Next, here I have summarized 4 key studies that related to my research. While reviewing the literature, I identified the clear research gap, which I will explain next. So I found that while many studies classifying reviews as positive or negative, they didn't um, they didn't go further to separate them into the UI and UX categories. Some focus on UI or UX individually, but not together. So in Sri Lanka, most of the researchers lies on the questionnaires, not the real user reviews from the App Store. And existing literature lack model explainability techniques to provide the transparency and trust in the automated classification of the user reviews. That can lead to formulation of my main research objective to classifying the negative reviews into UI and UX issues and identify the key features causing user dissatisfaction in the Sri Lanka leading mobile banking apps. The sub-objectives are first, to detect the negative reviews using the sentiment analysis and uncover the hidden themes through the topic model. Second, to identify the most accurate model for UI and UX classification and explain its decision using line. And third, to analyze the most common feature issues across the different apps that lead to the user dissatisfaction. So next, this process was divided into 3 main phases. So in the first phase, first user reviews are collected from the Google Play Store using the web scraping techniques for the 3 mobile banking app Apex, YZ, and then I apply the NLP techniques like stop word removal, to organization and lowercasing and to pre-process the data. And finally, the sentiment analyzing using the Vader model helped identify the positive and the negative reviews. To explore the user concern in more detail, negative reviews were filtered. So here this phase 2, I focus on the 3 negative reviews. First, TF-IDF vectorization was used to highlight the important words, and then the LDA topic modeling identified the dominant UI and UX themes. The final labeling was conducted through the manual evaluation by the domain expert using the predefined criteria. And next in the phase 3, phase 3, the trained 5 classification models such as KNN, random forest, and XGBoost, CatBoost, and the ANN by using an 80-20 testing and training and testing split. The model performance was evaluated using the performance matrices, and then the top accuracy model was explained using the line to interpret the prediction. And now move on to the results and findings. So here I will present the key outcome of this analysis. Let's look at one by one. So here this image gives the summary of total number of user reviews as well as the number of positive and the negative reviews for each banking apps. So next, So this table is show the base classifier performance across the all three banking apps. As we can see, the ANN model consistently outperformed the other and achieving the highest accuracy. So next, so look at the table that show the k-fold validation results that all the models with the k value of 5, the overall ANN performance best in app X and app Z, while the random forest stand out in app by. So the model performance slightly varies by the app. So next, after comparing both base and the k-fold results, we notice that ANN is strong in the app X and Z, but app by the ANN drop in the k-fold while random forest is performing better. So we tried to hybrid model and got the accuracy 79%, but still it didn't outperform the ANN. So finally, the ANN is confirmed as a best performant model across the all three banking apps for predicting the UI and UX related reviews. So next, so this table is compares ANN prediction with the line results for the same reviews. Since both gave the same UI and UX labels, it confirmed the reliability of the ANN while a line adds the interpretability and help explain why the model made this prediction, and alongside the comparison table. These line visuals show how the model interpret prediction for one review from each banking apps, so that highlighting the keywords that influence the classification as UI or UX. So next, so these are the images that illustrate the line-based explanation for the ANN model classification of the user reviews from the app XYZ. So next, so the thematic feature comparison process begin with the keywords extraction from the negative reviews of the each banking apps. So these keywords are identified using the LDA topic modeling techniques, which group frequently occurring the words into the topics. So then involve manually classifying these keywords into relevant meaningful key features categories as shown in this table. So next, so this graph is compares the key pain points identified in each banking app. As you can see, the general usability and the app performance are the common features struggle with all three banking apps. So next, so this graph representing the frequency heat map that visual the prevalence of negative reviews comments relies to UI and UX features in three banking apps. So next, let's look at the limitation and challenges faced in this research. First, due to the ethical concerns, the data was collected from the three leading banking apps, anonymized by as a bank XYZ. So the sentiment analyzing and the topic modeling were used for the key filter but not deeply analyzed or optimized. The challenges were encountered due to the unstructured and noisy nature of user reviews, including inconsistent language, slang, and varying reviews length, and real-time keywords validation, contact with the industry experts. Next, in the conclusion, this study dominates that properly analyzing, categorizing negative user reviews can lead to meaningful improvement in the Sri Lanka mobile banking app. By extracting and classifying the user reviews into the UI and UX issues using the effective topic modeling techniques, we are able to uncover the core area of the user dissatisfaction. The use of the line validation, our model's prediction, ensure the accuracy of keyword labeling and classification. The key concerns identify including the poor performance and the update issues and the error handling and usability challenges and login failures and transaction problem. Overall, this process model support the user-centered design approach and offer the strong foundation for the evaluating and improving the mobile banking apps experience. Next, look at the future works that could include analyzing multilingual reviews in Tamil, Sinhala, English, and we could also explore the other XAI techniques to improve the model interpretability and additionally investigating UI and UX improvement solution across different industries would provide the valuable insights. So next. These are the key reference that I use to support my research. And thank you so much for your listening. Thank you.
Okay, thank you. Thank you for sharing your great work. So any question or comments from the audience? Okay, so.
Even though you identify in the future section, usually in Sri Lankan context, people do reviews in the English and Singlish and Romanized Sinhala. So how you deal with that issue with when you are collecting data? Other thing is you have used the DF just to create the feature from the text. You use all way of doing the all type of technique. So why don't you use like modern data model word embedding techniques for feature representation of your blog post? Did you understand? Did you hear?
Yeah, I'm here. Hear you. Can you hear me?
Yes.
Okay, thank you for your question. And can you ask the question again? Sorry, I can't.
First one, even you identify as a future work. When you are collecting data, you may come across some plain English, Romanized Sinhala, and Singlish, like 3 versions of comments. How you deal with that one?
Yeah, when I collecting the data from the Google App Store, I only scrubbing the data. I only scrub the data that text content. So I filtered those text content only the English language question. I mean text only I scrubbed, and then after I do start my research. And in the future work, I will consider the Tamil and Sinhala also, because it's a most you are correct, because in Sri Lanka many of the people are using Sinhala and Tamil language, but in the future I will consider this point. Yes, thank you.
The question you use TIFT word embedding technique, but there are many more word embedding techniques available, and even transformer models use those techniques. So you can think about using those techniques in future when you are creating feature out of the text. Other thing, yeah, that's enough.
Yeah, thank you for your suggestion, sir. Thank you.
Okay, thank you. So actually, I have one more question about about the future work. So now you can try to use the AI technique to try to classify the reviews, and they may relate it to UI or UX. So how can this result help us to improve the future design of UI UX?
Sorry,
So,
can you?
So, I mean, have you studied how to use your current result to help in the design of the UI UX in the future? Can your result provide some guidance for the design in the design side?
Yeah. Sure. Because if you start the software app website, its start stage is a UI UX design. Then after you go to the development, testing, and deploy things. So when we are starting stage is it perfect, then the development and testing is most positive things. So it's better to most of the apps in the Google Play Store. They are deployed their apps, and there is a future updates also. They fixing their bugs, like if we deploy the app, then the real user, when using the app, we can identify what they are feel and what they what they face the struggle to use that app or web. So it's better to identify the UI and UX issues. And next update, the developers easy to focus on which feature we only focus. But in my research, I focus UI and UX things, and in the future, it is possible to which feature is we focus in UI. We are focused on colors or navigation and the auto layouts things, and UX it's slow things and transaction poor. Those are the things in UX side. So in future, I will which future is specifically we want to improve that particular app or web. Thank you.
Okay, thank you. So let's move to the next presentation. And the presenter is Varitaya, and the work's name is Oil Spill Identification in Satellite Imagery using Transformer-based Deep Learning Models. Thanks.
Hello everyone, my name is Rataya Pipati from Rangsit University, Thailand. Today I am presenting our research titled Oil Spill Identification in Satellite Imagery using transformer-based deep learning models. This work focuses on using advanced deep learning techniques to detect oil spills from satellite images, particularly synthetic aperture radar or SAR images. Let me begin with the background and motivation. Oil spills continue to pose serious threats to marine ecosystems. SAR imagery is highly useful because it works under all weather and lighting conditions. However, the challenge lies in its noise and the presence look-alike phenomena, such as low wind areas and algal blooms that often confuse detection systems. So our research proposes a novel deep learning pipeline that integrates image enhancement and transformer-based classification to improve detection accuracy. We have set 4 main objectives for this research. One is to test whether enhancing SAR images helps improve classification accuracy. 2 is to compare to enhancement methods like real SR and gradient. And next is to evaluate for transformer-based model for classification. And last is to identify the best performing combination for practical deployment in real-world monitoring systems. Now let me walk you through our methodology. The pipeline has 2 main stages. One is image enhancement. We use the real SR and gradient, both based on swing architecture. Classification we use 4 different transformer models like with small, date based, and string transformer. We evaluated enhancement quality using PSNR and SSIM, and classification accuracy we use precision, recall, and F1 score. About the dataset, we used the SAR oil spill detection dataset, which contains 1,112 SAR images of 1250 by 650 pixels. The dataset includes 5 classes like sea surface, oil spill, lookalike, ship, and land. It's split into 80% for training and 20% for testing. Each image is paired with RGB mask and 1D label maps to aid supervised learning. About this, both real SR and gradient are based on the swing architecture. The model has 3 stages. The first is shallow feature extraction. Second is deep feature learning using residual swing transformer blocks. And the third is image reconstruction. The real SR focuses on super resolution, while gradient focuses on denoising without changing image size. And about the For classification, we used vision transformers, ally CNNs. These models treat images as sequences of hashes and use cell extraction mechanisms. We evaluate four models such as with small, D8-based, and swing transformer. Each of these models has different strengths in handling feature extraction and generalization. Well, and let's now move to the result, starting with enhancement. The RealSR produce sharper visuals, but may introduce introductive effects. Like gradient has better IM scores, meaning is better for structural consistency. This difference affects classification downstream. And about the visual comparison, this slide compares classification results in RealSR enhanced images. The model misclassified a region as sheep when it wasn't. But with gradient, that error was avoided. So enhancement methods significantly affects how accurately the model interprets subtle visual cues. And about the classification result, we test each enhancement method across all transformer models. The best result from gradient plus state-based that achieving an average A1 score of 93.2%. The width-based model consistently give the lowest score across both enhancement types. Ship class was the most difficult, but gradient improved performance even in that category. And to conclude, our study clearly shows that image enhancements play a vital role in boosting the performance of oil spill classification using its AI imagery. Without enhancement, even powerful models like vision transformers struggle with subtle or visually ambiguous features. Among the two enhancement strategies, gradient consistently performed better than RealSR, especially when it came to preserving the structural integrity of the image, which is critical for detecting complex features like lookalikes or small oil spill traces. And when gradient was paired with date-based, we achieved the highest classification performance across all classes with a particularly strong event score of 93.2%. This combination not only offers high accuracy but also stability across different image types and conditions, making it a strong candidate for practical deployment in real-world maritime monitoring systems such as real-time coastal surveillance, environmental protection task, or automatic detection modules on patrol vessel. And that brings us to the end of our presentation. We hope this work contributes meaningfully to the field of remote sensing and environmental monitoring. Thank you very much for your attention, and we now welcome any questions.
Thank you. So any questions or comments? Okay, so personally, I think this is a useful topic. And I think in this work, the author has already provided some good solutions. But I still have one question about the data or the solution. So have you tried to study the extreme weather conditions like typhoon or dust storm? So if such a weather conditions with such a extreme weather conditions, can you still detect the oil spill?
Okay, can you hear me? Okay.
Yes, yes.
Thank you for the question. And about the data set, because of the limitation of the data set, we haven't tried to look at about the weather that much about the typhoon, or somehow that is hardly to see because the data set that we use is come from the public is public.
Okay, thank you. So I have a suggestion. Maybe we can try to add some, one more label to the data set. It means that we cannot detect, the unknown results, something like that. So for example, you can have the yes or no, and you have an unknown between name. So when the model fails to detect the result, you can try to output something like an unknown. Yeah. So any other questions? Okay, so thank you. Thank you for your great presentation.
Thank you so much.
Okay, so let's move to the last presentation today. The name is Subject-Wise Impact of VAK Learning Style on Student Personalization Using Ensemble Learning. And then the presenter is Sarah Song. Thank you.
Our research title is Subject-Wise Impact of Work Learning Styles on Student Personalization Using Ensemble Learning. These are our authors and co-authors details. The presenter is Mr. Ketharson. These are the contents. Let's see this one by one. Let's see about the introduction of this background. Personalized learning has emerged as the gold standard in modern education, emphasizing the importance of identifying individual learning patterns and implementing tailored teaching strategies. The work model stands out as an accessible yet powerful framework for determining learning preferences and optimizing educational experience. Traditional approaches to learning style assessment have relied on self-reporting inventories or educator observations, both methods facing inherent methodological constraints and potential biases. Machine learning approaches to learning style prediction. Traditional ML offers data-driven prediction of learning styles based on behavioral patterns and assessment outcomes, reducing reliance on subjective methods. Key challenges: dependency on extensive quality data set for accurate prediction. The black box nature limiting results interpretability and the trust. Ensemble learning methods like bagging, boosting, stacking present promising solutions to improve prediction accuracy and reliability through their application to work style prediction remains unexplored. Let's see about the problem statement. There is a lack of research in Sri Lanka examining how work learning styles affect student performance in core subjects in secondary education. The study focuses on key subjects like mathematics, science, English, history, religion, and mother language, singular or Tamil. In secondary schools, learning styles of individuals are not always considered in teaching, which results in poor learning and participation among students. The proposed research will provide evidence-based recommendations for adopting personalized teaching methods suited to students' learning styles in Sri Lankan secondary education. Let's move to the literature review. The table 1 shows summary of related studies and the proposed research. Let's move to the methodology part. Data collection. Two data sets used to analyze student learning style. One is Gaggle data set. It contains 1,210 responses with 5 questions per work learning style on a 5-point Likert scale. The Google Forms survey collected work learning preferences from Sri Lankan secondary students using 15 Likert questions across 6 courses. Those are Sinhala or Tamil, English, Math, Science, History, and Religion. Combine these two for a comprehensive data set on learning preferences. The figure 1 shows proposed research methodology for phase 1. Let's talk about the phase 1 and the phase 2 of the methodology. This study followed a two-phase methodology. Phase 1 involved data collection, data processing, data splitting, and data sampling, followed by application of ensemble methods such as bagging, boosting, stacking to identify the optimal model for work classification. In phase 2, the selected model was used to analyze how work learning styles influence students' performance in core subjects, COSA, mathematics, science, English, history, early and the mother tongue, Tamil or single. The overall methodology is illustrated in figure 1 for phase 1 and figure 2 for phase 2. Let's move to the results and findings part. Individual machine learning and deep learning model prediction. Table 2 shows individual machine learning and deep learning model performance. Among individual machine learning models, random forest gave the high accuracy of 85.22%. Among deep learning models, FNN gave the high accuracy of 86.47%. Let's see about the ensemble model prediction. Bagging predictions. This study uses a bagging class to form a bagging ensemble of multiple base learners derived from dictionary, KNN, support vector machine, LR, RF, and extra trees. The extra trees model came out on top with the bagging classifier test accuracy of 89.59%. It means this was the best model in this setup. Let's see about the stacking predictions. Stacking model 1 combines base models SPM, KNN, extra trees, DTC with LR as the meta classifier, ensuring accurate predictions through ensemble learning, achieved 90.50% test accuracy. Stacking model 2 combines FN and RF as base learners with XGBoost as the meta classifier. It's achieving 91.70 test accuracy. Boosting predictions among AdaBoost, XGBoost, SPBoost, CatBoost, and Light GBM SPBoost. SPBoost achieved the highest accuracy of 89.44%. The table 3 shows the ensemble model performance. You can see through the table 3. Let's see about the impact of work learning styles on core subject performance. This is an assessment aligned with stacking model 2 related to the influence of learning styles on achievement across this area. The results will indicate the required differentiated instructional strategies relative to what a student like to learn to be taught more successful. The figure 3 to 8 present the ggplot histogram illustrating how work learning styles influence students' performance across this 6 core subject area. As shown in the figure 9, results revealed distinct learning style preferences by subject. Kinesthetic dominance in mathematics, it's around 41.4%, and science also 47.8%. Auditory preference in mother language is around 40.9%, and history around 37.5%, and balanced distributions in English and the region. Let's see about the limitation and challenges. The study is confined to the major subjects of secondary education in Sri Lanka. These are mandatory subjects, and students must pass them in order to be considered academically successful. Elective subjects are also purposefully left out of the study, as their assessment in the context of the given research improvement poses quite a challenge. In conclusion, stacking, boosting, and bagging created a variety of ensemble models. Stacking achieved a prediction accuracy of 91.7%, while XGBoost recorded 89.44%, and extra trees with bagging classes 89.59%, all outperforming the traditional ML model. The research essentially involved analyzing the influence of each work learning preferences on student engagement and student performance in in the major subject. Findings show that from a better stance of one's own learning styles, it increases the potential for student engagement and student performance capabilities in this subject area. This research allows teachers the potential to change their teaching styles and unit plans to be more effective and more customized for greater student success. Let's see about the future. Future research can build upon this study by integrating the developed ensemble model with learning management system to focus and adapt to learning style dynamically. These are the references. And thank you.
Okay, thank you. Thank you for the great sharing. So any questions or any comments for the author? Okay, so in the limitation, I have saw that the authors say that the data is from the single specific region. So can you share some idea about how can we generalize the method to like the students in other regions? How can we do these things? We have to calculate, I mean, correct the data set for training, or is it possible for us to use some technology like domain adaptation to shift the model to a specific new domain? Yeah, see.
Hello, can you hear me?
Oh, yes, yes.
Can you ask me again that question?
So my question is that in this work, we just use the data from the specific region for study and training, right? So if we want to adapt the same method to other students in other regions, how can we do these things? We have to correct, I mean, more data set from the specific region, or we can try to use some specific technologies like domain adaptation to solve this problem. Do you have any idea can share?
Yeah, it's in future studies we can consider about this, but now this study we consider in Sri Lanka secondary education. So we can apply those in the future work.
Okay. I have another question. So do you think the method can be generalized to other student levels like high school student or the college students in the future? So
Yeah, we can adapt high studies or universities also, but now we consider in secondary education. But in future, we can consider about this, and also we can develop optimal models for each specific domain of subject. It's better we analyze those.
okay, thank you. Thank you. So any more questions? Oh, so if no more questions, we have finished today's presentation, and let's walk the chairs for sharing.
Yeah. Thank you very much. Yeah, that's the end of our tech. Yeah, I think it's fine. Yeah, that's the end of the technical sessions of APAN Conference 2025. And if you have any questions, comment or suggestions, then we can have a small discussion. 5 minutes, 10 minutes, if you have any questions or anything. Right then, thank you very much. And I must thank our professors for chairing this session, Dr. Leah and Dr. K. Right. Okay, thank you very much for your support, and we will share appreciation letters after this conference. Okay. And the students, thank you very much for your work, and your work will be published in Springer Journal again, and subjected to corrections. And yeah, thank you. And yes, that's it. And again, my supporting staff, Imam, Saiko, Celine, and Mujtaba. Thank you very much for your support as well. And yes, one last announcement. This one. So we next time we are planning to have the conference in Auckland, New Zealand. It will happen in around August 2026, and we plan to open the submissions in April 2026. Right. So keep the dates, and also if you can scan this QR code, then you can also register in the portal. So then we can contact you by that time, and also you can join as staff members like chairs, session chairs, or technical program committee chairs, right? So we have available positions, so we can recruit you for those positions as well. That depends on APAN, so I'm just managing the conference. Okay, thank you. Right, then thank you very much, everyone. All the best, and have a safe journey back to your countries. Thank you very much. Okay.
Thank you.